The universe is 13.8 billion years old, right? But the light hitting you right now has been travelling since long before stars, galaxies, or planets even existed. In this video, we're going to unpack how that's possible, why some photons are older than almost everything in the cosmos, and how that mind-bending fact is still perfectly consistent with the laws of physics. So first, you need to clear up the word older, because that's where your brain gets twisted. When people say this light is older than the universe, that's not literally true in a physics sense. The age of the universe, that 13.8 billion year number, is defined as the time since the Big Bang. Nothing inside that space-time can have an age greater than that. Not a star, not a black hole, not a photon. What they really mean, even if they don't say it clearly, is that this light is older than most of the structures in the universe. Older than stars, older than galaxies, older than galaxy clusters, older than the Milky Way, older than the solar system, older than Earth. So how do we get that 13.8 billion year age in the first place? This is not guesswork or a vibe, it's measured. We look at several things at once. First, we measure how fast the universe is expanding today by tracking how galaxies move away from us. That gives us the Hubble constant. Second, we map huge numbers of galaxies over billions of light years, and we see how matter is clumped on the large scales. Third, we measure the cosmic microwave background, the faint microwave glow that fills the entire sky, which is leftover radiation from the early universe. When you fit all of those data sets with a single model of how the universe expands and changes over time, the numbers line up around 13.8 billion years of cosmic history. Now, inside that 13.8 billion years, the oldest photons we can actually see are the ones that make up the cosmic microwave background, the CMB. These photons were last scattered, basically released, when the universe was about 380,000 years old. Before that, the universe was so hot and full of free electrons that photons kept bouncing around and couldn't travel far. At around 380,000 years, the universe cooled enough for electrons and protons to combine into neutral hydrogen. The fog cleared, and light suddenly could move almost freely. The photons from that moment are still around today, still travelling at about 300,000 kilometers per second, around 186,000 miles per second. So you take the age of the universe, about 13.8 billion years, and subtract that early 380,000 years. You get roughly 13.7996 billion years. That is the travel time of the oldest photons we can detect. For almost the entire age of the universe, these same individual photons have been in flight. No breaks, no pauses, just moving through space that is expanding under them. Sunlight takes about 8 minutes to reach Earth. Across 150 million kilometers, about 93 million miles. These CMB photons have been traveling not for minutes, but for billions of years. In terms of age, they are just a tiny fraction younger than the universe itself. Here is where the older than everything feeling really kicks in. When those photons started traveling, there were no stars, no galaxies, no planets, no heavy elements like carbon or oxygen or iron. The universe was just a hot gas of hydrogen and helium, with tiny variations in density. The big structures you're used to seeing in space images, spiral galaxies, elliptical galaxies, galaxy clusters stretching millions of light years, all of that formed later. The photons were already flying while all of that was still in the future. To put that into a simple comparison, take the whole age of the universe and call it 100%. Those CMB photons were released when the universe was at about 0.003% of its current age. That is not 3%, that is 0.003%. Everything you see in modern astronomy, from the Milky Way to the Andromeda Galaxy to massive clusters, sits in the remaining 99.997% of the timeline. You live in a very late chapter, the photons started their journey near the beginning. So when you hear fossil light, that's what people are talking about. The light is like a record from a very early state of the universe, while most familiar objects are newborn in comparison. Galaxies are late products of gravity slowly pulling matter together. Stars are local nuclear furnaces that turn on and off over millions or billions of years. Planets are leftovers from star formation. But the background radiation has been there almost the entire time, just getting stretched to longer wavelengths as the universe expands, shifting from visible and infrared light down into microwaves. That sets up the real core idea of this whole video, the thesis you're going to keep coming back to. You are surrounded right now by light that carries information from epochs that feel almost unreal in terms of age. This light is not older than the universe in a strict sense, but it is older than almost everything that makes the universe look the way it does now. When you walk outside at night, you're not just looking at stars a few hundred or a few thousand light years away. You're sitting inside a bath of ancient photons that have been travelling for nearly 13.8 billion years, crossing distances measured in tens of billions of light years in today's units, which is on the order of 10 to the 26 meters, or about 10 billion trillion miles. So the natural next question is this: if light is that old, at what point in the Big Bang timeline did it actually become possible for photons to exist in a way that matters for us? When did the universe go from no meaningful light to light that can travel freely for billions of years? To answer that, you have to roll the clock all the way back to the very first fractions of a second after the Big Bang, into an era where space-time itself was in an extreme state, and even the word photon stops being simple. How far back can you push the idea of light before the word stops making sense? If you really want to know when light could first exist in any useful way, you have to go right to the edge of our physics, to a time when even calling something a photon is basically wrong. At the very start, you hit what's called the Planck era. That's the first tiny slice of time after the Big Bang, up to about 10 to the power minus 43 seconds. That number is so small it's basically 0 plus a bit. In that era, the energy scales are around 10 to the power 19 giga-electron volts. Those energies are far beyond anything we can make in a particle accelerator, far beyond anything we can test in the lab. At that point, space-time itself is not smooth and calm, it's dominated by quantum gravity effects we don't fully understand yet. And this is the key point. In that regime, talking about light the way you talk about light from a bulb or from the sun doesn't really work. A photon is supposed to be a stable, well-defined particle of light with a clear wavelength and frequency. In the Planck era, the universe is too hot, too dense, and too chaotic for that. The whole idea of a single photon flying along on a clean path is just not meaningful. Our current theories break down there, and any picture you draw is more guess than calculation. So if the earliest instant is too extreme for normal photons, the next question is, when does light start to behave in a way we would at least recognize as real, even if it's still not free to travel across the universe? Very soon after the Planck era, the universe expands and cools enough for our standard physics to kick in. We move into a phase where we can talk about known particles, quarks, gluons, electrons, neutrinos, and yes, photons. This is still within fractions of a second to the first few minutes after the Big Bang. The temperatures are in the trillions of Kelvin, which is way beyond the core of any star, way beyond anything in the modern universe except maybe near some black holes. In this phase, photons do exist, but they are not usable in the way you might think. They are constantly interacting with charged particles, being absorbed, re-emitted, scattered in every direction. The universe is like an extremely dense plasma. A photon cannot just move in a straight line for long, it travels a tiny distance and then hits something. So yes, there is light, but it is trapped. There is no clear view across space, no line of sight, no way for that light to carry a clean image or a clean signal over large distances. So that raises the next step. If photons exist but are trapped, what else is happening in those early minutes that sets the stage for everything that comes later, including stars, galaxies, and eventually you? A few minutes in, the temperature of the universe has dropped to around 1 billion Kelvin, still incredibly hot, but now cool enough for a crucial process to happen. Protons and neutrons, which were flying around separately before, start to fuse together. They form helium nuclei along with tiny amounts of deuterium, which is heavy hydrogen, and lithium, This is called Big Bang nucleosynthesis. This phase only lasts a short time, but it leaves a permanent mark on the universe. Because of the conditions back then, you end up with a very specific mix of elements, roughly 75% hydrogen and 25% helium by mass, with just traces of those heavier light elements. When astronomers look at the universe today and measure the composition of very old simple gas clouds, they see almost exactly those ratios. That is one of the strong pieces of evidence that this early universe picture is right. But even during nucleosynthesis, the photons are still trapped in the plasma. They are constantly bouncing off free electrons and other charged particles. So the obvious next question is, when does that change? When do photons finally get released and start the journey that will last almost 13.8 billion years? Now you fast forward a lot. Not fractions of a second, not minutes, but hundreds of thousands of years. The universe keeps expanding, keeps cooling. By the time you get to about 380,000 years after the Big Bang, the temperature has dropped to around 3,000 Kelvin. For comparison, that's roughly half the temperature of the surface of the Sun, which is about 5,800 Kelvin. At this point, something big happens. Electrons and protons finally slow down enough to combine and form neutral hydrogen atoms in huge numbers. When that happens, the universe goes from being opaque to being transparent. Before this, free electrons were everywhere, and photons could not travel far without hitting one. After recombination, most of those electrons are locked inside atoms, and the number of free electrons drops sharply. Suddenly, photons can travel long distances without constantly scattering. This moment is often called photon decoupling, or the big unlock for light. The photons that were around at that time moving through this newly transparent universe are the same photons we detect today as the cosmic microwave background. Back then, their wavelengths were in the visible and infrared range, more like a glowing orange-red fog. Over billions of years, as the universe expanded, their wavelengths were stretched into the microwave range. Their color shifted down, their energy dropped, but they are still the same individual photons. So now you hit the crucial point for this entire video. What is actually older, the light or the things you see shining in the sky? No star you can see, no galaxy you can point a telescope at, and no planet you can ever stand on existed before that transparency moment, before about 380,000 years after the Big Bang. Stars need time to form from collapsing clouds of gas. Galaxies need even more time, as gravity slowly pulls matter together at larger scales. Planets need stars to form first, then disks of gas and dust around those stars, then collisions and growth inside those disks. All of that unfolds after the photons of the cosmic microwave background have already been released and started travelling. Those CMB photons are older than every star, older than every galaxy, older than every planet. They define the oldest light you can ever hope to see with any telescope, because before that, the universe simply did not let light travel freely. So now you're in a strange situation. You live in a universe where the oldest light is locked in at about 380,000 years after the Big Bang, and nothing you can observe with the electromagnetic radiation is from an earlier time than that. That sets up the next big question. If that ancient glow is really the oldest light you can touch, how exactly do we measure it today, and what does it tell us about the universe that came after? How can the universe feel so cold today when it started out unimaginably hot? If the Big Bang was this blazing beginning, why does the sky in microwaves read just 2.7 degrees above absolute zero, basically almost as cold as physics allows? If you could point a perfect microwave thermometer at any direction in the sky, you'd measure about 2.725 Kelvin over and over again. That's only 2.7 degrees above minus 273.15 degrees Celsius, which is absolute zero. In Fahrenheit, that's about minus 454 degrees. It sounds like nothing is happening, just cold emptiness. But that pink, uniform glow is the stretched out, cooled down afterglow of the universe, when it was about 3000 Kelvin, hot enough to glow like a red-orange furnace. Back at recombination, those photons were in the visible and infrared range, more like the light from a very hot metal surface. Over 13.8 billion years of expansion, space itself stretched, and their wavelengths got stretched by a factor of roughly 1,100. So a photon that started with a wavelength 1,000 times shorter is now a microwave with a wavelength of around 2 millimeters, about 0.08 inches. Same photon, same speed, but the universe pulled it out to a lower energy state just by expanding. So the first thing to get clear is this: that cold microwave glow you can't see with your eyes is not new light, it's ancient light that has been weakened and cooled by the growth of the universe itself. That naturally raises the question, how do we know this isn't just some random radio noise? How do we know it really is the Big Bang's afterglow? In the late 1980s and early 1990s, a satellite called COBE, the Cosmic Background Explorer, was launched to measure this background precisely. One of its jobs was to check the spectrum of the sky, meaning how bright the radiation is at different wavelengths. If the Big Bang model is right, the CMB should follow what's called a perfect blackbody curve, the ideal spectrum of an object that absorbs and emits radiation perfectly at a single temperature. COBE's result was brutal and clean. The CMB spectrum matched a perfect blackbody to better than 1 part in 10,000. That is insanely precise by astrophysics standards. It basically said, yes, the entire sky is glowing like a single object at 2.725 Kelvin, and it's almost flawless. That was a huge confirmation that we are really seeing the cooled down afterglow of the early universe, not some weird foreground effect or local noise. But COBE did more than that. It also checked how smooth that glow is across the sky. At first, it looked almost perfectly uniform. Later missions, WEM-AP and then Planck, with sharper resolution and better detectors, took this to the next level. They mapped tiny temperature differences in the CMB down to levels of about 1 part in 100,000. So instead of the sky being exactly the same temperature everywhere, it's 2.725 Kelvin plus or minus a few tens of microkelvin, a few millionths of a degree. Those ripples don't sound like much, but they are the key. So the obvious follow-up is, why should you care about tiny temperature bumps of a few millionths of a degree? What do they actually mean physically? Those little temperature variations correspond to density variations in the early universe. Slightly hotter spots are a bit less dense, slightly cooler spots are a bit more dense. The differences are tiny, around 0.001% from place to place, but that's enough. Gravity loves small imbalances. Over billions of years, those slightly denser regions pulled in more matter, grew heavier, and attracted even more material. The slightly emptier regions lost out, matter flowed away from them. Given enough time, that slow, relentless process turns those little bumps into the massive structures you see today. Galaxy clusters, filaments and voids stretching across hundreds of millions of light years, which is on the order of 10 to the power of 24 meters, or roughly 600 quintillion miles. The cosmic web you see in simulations, the giant network of galaxies spanning the observable universe, started as these tiny, almost invisible wiggles in the CMB map. So when you look at one of those famous Planck or WEM-AP maps, with red and blue spots showing temperature differences, you're not looking at random noise. You're looking at the blueprint for every galaxy that would ever form. That leads straight into the next hard question. When we say the CMB light is older than galaxies, how big is that gap? Are we talking about a small difference or something huge? Here are the numbers. The CMB photons have been travelling freely since about 380,000 years after the Big Bang. The age of the universe now is about 13.8 billion years. So the light you're seeing in the CMB has been on the road for roughly 13.7996 billion years. The oldest galaxies we have detected so far, using telescopes like Hubble and the James Webb Space Telescope, appear at redshifts around 10 to maybe above 13. That corresponds to times a few hundred million years after the Big Bang, roughly 300 to 400 million years, and look back times of around 13.4 to 13.5 billion years. So in simple terms, the oldest galaxies we can see are younger by a few 100 million years than the CMB light. That means the photons from the CMB predate those galaxies by something like 300 to 400 million years. In human terms, that's an enormous gap, longer than the entire time complex animals have existed on Earth. In cosmic terms, it's still a big chunk of the early timeline. So yes, when you say this light is older than galaxies, that's not drama. That's literally true in terms of travel time. Once you accept that, there's another step that makes it feel even more intense. This ancient light is not something far away that you need a super telescope to access. It is everywhere, including right where you are sitting right now. Every second, trillions of CMB photons pass through your body. They come from all directions. They don't care if you're inside a house, in a city, or in deep space. They're extremely low energy, so you don't feel them, you can't see them, but they're there. Each photon has been travelling for almost the full age of the universe, crossing what we describe in today's coordinates as tens of billions of light years. In metric, that's roughly 10 to the power 26 meters, or about 10 billion trillion miles. So you're not just next to the oldest light, you're immersed in it all the time. You're basically the endpoint of a journey that started when there were no stars, no galaxies, nothing like the Milky Way, just a hot gas and those tiny ripples in density. When one of those photons hits a detector in a satellite or indirectly affects electronics on Earth, that's the end of a 13.8 billion year path. And that sets up the next big tension. If this ancient light is everywhere, and it has been travelling for almost 13.8 billion years, how do we connect that travel time to the actual distances we talk about? Like 10 billion light years, 46 billion light years, the size of the observable universe. Because now you run into something that sounds impossible. How can we talk about distances larger than 13.8 billion light years if the universe is only 13.8 billion years old? How can something be 10 billion light years away and at the same time be 10 billion years old in your telescope? When you hear that number, your brain usually just flags far, but in cosmology, light year is distance and time fused together. 1 light year is the distance light travels in 1 year, about 9.5 trillion kilometers, around 6 trillion miles. So if a galaxy is 10 billion light years away in look-back time, that means the photons you are catching today have been traveling for 10 billion years straight. That also means when those photons left, the universe itself was younger. The universe is about 13.8 billion years old now. If a photon has been travelling for 10 billion years, it started its trip when the universe was about 3.8 billion years old. So every time you look at a distant galaxy, you're seeing it not as it is now, but as it was when that light was emitted. Your telescope is not showing you the present universe. It is showing you a stacked timeline, nearby objects almost now, farther objects billions of years in the past. Bigger mirrors and better detectors literally push you further back in time because they can pick up fainter, more distant, older photons. That leads straight into the confusing part. If light is limited by the age of the universe, how can we talk about an observable universe that has a radius of about 46 billion light years? That's about 4.3 times 10 to the power of 26 meters, or roughly 270 billion miles. Light has not had 46 billion years to travel. The universe is only 13.8 billion years old. So what is going on? The answer is expansion. While a photon is in flight, space itself is stretching. The photon always moves at the speed of light, about 300,000 kilometers per second, 186,000 miles per second, relative to its local space, but the distance between where it started and where you are now is not fixed. When the photon left, the region it came from was much closer. During the billions of years it took to reach you, the universe expanded and dragged that region farther away. So the light travel time might be 13.5 billion years, but the current distance to that source right now can be 30, 40, even 46 billion light years. So when cosmologists say the observable universe has a radius of about 46 billion light years, They mean if you froze the expansion today and measured the current distance to the farthest stuff whose light is just reaching us now, that's the number you'd get. The travel time is still capped by 13.8 billion years, but the present-day distance is larger because the fabric of space has been stretching the whole way. That raises a practical question. If you can't send a measuring tape out there, how do you actually know how far these galaxies are and how far back in time you're looking? The key tool is redshift, usually written as Z. When light travels through an expanding universe, its wavelength gets stretched. The more the universe has expanded while that photon was in flight, the longer its wavelength becomes by the time it hits your detector. Redshift is basically a measure of how much that stretching has happened. If the wavelength got doubled, that's one redshift range. If it got stretched by a factor of 11, that's a much higher redshift. Astronomers use known spectral lines, for example from hydrogen, to measure this. Hydrogen has a specific ultraviolet line at a fixed wavelength. If you see that same pattern way shifted into the infrared, you can calculate how much the light has been stretched, and that gives you the redshift. Roughly, a galaxy at redshift about 1 sits around halfway back in cosmic time. Redshift around 10 pushes you right into the cosmic dawn, the era when the first generations of galaxies were lighting up. The cosmic microwave background itself comes from redshift about 1100, an extreme stretch from orange-red light to microwaves. So redshift is not just a colour shift, it is a built-in clock. The higher the redshift, the closer you are to the early universe, to the era when those first free photons were released. Then comes the obvious follow-up. Who is actually catching this insanely stretched, faint early light right now? That's where the James Webb Space Telescope, JWST, comes in. JWST has a mirror 6.5 meters across, about 21 feet, much larger than Hubble's 2.4 meters. It is tuned for infrared light, which is exactly where those high redshift galaxies show up, because their originally ultraviolet and visible light has been stretched into the infrared by expansion. JWST is already finding galaxies at redshifts above 10, and candidates even higher, maybe pushing toward 15 or more depending on how the data shake out. Those galaxies are being seen as they were when the universe was only a few 100 million years old, not even 1 billion yet. The photons hitting JWST's detectors left those galaxies long before Earth existed, long before the Sun existed, before the Milky Way looked anything like it does now. At that time, the material that would someday become the solar system was just a tiny part of a generic gas field, not even organized into a disk, not even turned into dust grains around a star. So if JWST can see back that far, you might ask, why not go even further? Why not build an even bigger telescope and look before those CMB photons were released straight into the first second after the Big Bang? Here is the hard wall. Before about 380,000 years after the Big Bang, the universe was opaque to photons. The gas was a hot plasma filled with free electrons, and photons could not travel far without being scattered. Their mean free path, the average distance they could move before hitting something, was tiny compared to cosmic scales. So no matter how big your telescope is, you cannot see through that early plasma with light. There is no clean line of sight, no clear image from that time, because photons were constantly being absorbed and re-emitted. If you want information from earlier than that, you have to switch to different messengers. Relic neutrinos from about 1 second after the Big Bang, or primordial gravitational waves from a fraction of a second after the Big Bang, could in principle carry information from those eras, because they interact much more weakly with matter, and can travel through that dense plasma almost untouched. But for electromagnetic radiation, for light in any part of the spectrum, the universe itself has drawn a line. You get no direct picture from before recombination. So the oldest light you will ever get, with any telescope, is locked to that 380,000 year mark. Everything older than that is hidden behind an opaque wall for photons. And that brings up a new tension. If we can only see back to 380,000 years, what happened in the long stretch between that moment and the first star switching on, in the era when the universe was transparent, but still dark, with no galaxies and no starlight at all. How do you have a universe that's transparent, full of light, but still basically dark? Once those first photons from recombination are released, the fog clears, but for a long time nothing in the universe is actually shining in the way you think of as light. That strange in-between era is where the idea of light older than any star you know really locks in. Right after recombination, around 380,000 years after the Big Bang, the universe is finally clear to photons, but it is not bright. There are no stars yet, no galaxies, no planets. The gas is mostly neutral hydrogen and helium, spread out, slowly cooling and very gradually starting to clump under gravity. You still have the cosmic microwave background, that 3000 Kelvin afterglow that will slowly cool down to 2.7 Kelvin over billions of years, but that glow is smooth and boring in visible light terms. If you could somehow stand in that universe with human eyes, you wouldn't see a night sky full of stars. You'd have a kind of dim, uniform red-orange fog at first, and as time goes on and wavelengths stretch, that fades out of the visible completely. This stretch of time from roughly 380,000 years to something like 100 to 200 million years after the Big Bang is what cosmologists call the cosmic dark ages. Dark doesn't mean there are no photons at all, it means there is no starlight, no bright point sources, no galaxies lighting things up. There is just neutral gas, the ancient microwave hiss of the CMB, and the slow pull of gravity starting to do its long, patient work. So then the obvious question is, what finally snaps the universe out of this dark, quiet state? What turns the lights on for real for the first time over tens of millions of years? Those tiny, overdense regions you saw as ripples in the CMB map start to collapse. Dark matter and gas fall together, forming the first small halos where gravity is strong enough to pull hydrogen into tight clumps. Inside those clumps, the gas compresses, heats up, and eventually reaches the point where nuclear fusion can start. That's the birth of the first stars. These first stars are called population 3 stars. They are very different from the Sun. The Sun has heavier elements like carbon, oxygen, and iron mixed in, made by earlier generations of stars. Population 3 stars formed from almost pure hydrogen and helium straight from the Big Bang, with essentially no heavy elements. That changes how they behave. Simulations suggest they're huge, maybe 30 to 300 times the mass of the Sun. Some might be even more extreme. Their surface temperatures climb into the tens of thousands of Kelvin, much hotter than the Sun's roughly 5,800 Kelvin surface. In size, some may stretch to radii of tens of millions of kilometers, tens of millions of miles, compared to the Sun's radius of about 700,000 kilometers, roughly 430,000 miles. They are bright, unstable, and short-lived. Many of them probably burn through their fuel and die in just a few million years, which is nothing on cosmic timescales. So once these monsters light up, what does all that intense radiation actually do to the rest of the universe? Those first stars pump out huge amounts of ultraviolet light, much more energetic than visible light. Ultraviolet photons have enough energy to knock electrons off neutral hydrogen atoms. So as more and more population 3 stars form, their radiation starts to rayonize the universe. The neutral hydrogen that filled space after recombination gets broken back into protons and electrons in many regions. This era is called the Epoch of Rayonization. It happens roughly between redshift 6 and redshift 10, which corresponds to about 500 million to 1 billion years after the Big Bang. It is not an instant flip, it is a messy, patchy process. Bubbles of ionized gas grow around groups of young galaxies and first stars, then expand, then overlap, until eventually most of the intergalactic hydrogen is ionized again. We don't just guess this, we see its fingerprints. When astronomers look at very distant quasars, bright sources powered by black holes, they see that the light passing through the early universe gets absorbed in a way that tells you how much neutral hydrogen is still around. On top of that, subtle polarization patterns in the CMB show that some of those ancient photons scattered off free electrons released during reionization. So the first stars literally leave marks both on later light and on the oldest light. Now line up the timelines. The CMB photons were released at about 380,000 years after the Big Bang. The first stars don't show up until maybe 100 to 200 million years after the Big Bang. And the bulk of reionization wraps up a few hundred million years after that. That means the CMB photons you detect today were already travelling freely for hundreds of millions of years before the first star ever turned on. So when people say this light is older than any star you know, that is exactly what they mean. Those CMB photons started their journey in a universe with no stars, then travelled through the cosmic dark ages, then through the era when the first massive hot population 3 stars exploded into existence, then through reionization, then through billions of years of normal galaxy evolution, and they are still going. When you measure them now, you are literally sampling radiation that predates every star in the sky, including the Sun, including every star in the Milky Way. That naturally leads to the next challenge. How close can we actually get, with real telescopes, to that moment when the first stars and galaxies switched on? And how does that compare to the age of the CMB light in your detectors? This is where the James Webb Space Telescope comes in again. JWST is already picking up galaxies at redshifts above 10. That means you're seeing those galaxies as they were when the universe was less than about 500 million years old, maybe 300 or 400 million years, depending on the exact redshift. The photons hitting JWST today left those galaxies when there were no planets like Earth, no solar system, and the Milky Way itself was in a very early primitive state. Those photons have travel times of around 13.3 billion years or so, which is mind-blowing on its own. But you have to compare that to the CMB photons. The CMB light has been travelling for almost 13.8 billion years, so even the earliest starlight you can see with JWST is still a few hundred million years younger than the background radiation. In other words, you are looking at teenage galaxies superimposed on a background of photons that are basically as old as the universe itself. This is where that older than the universe feeling sneaks in. You're dealing with signals that have survived the dark ages, the first stars, the formation of galaxies, the building of clusters, the entire history of the Milky Way, and the full lifetime of the solar system. By the time they hit a detector or pass through your body, they have crossed an unbroken chain of cosmic eras that together define almost everything that has ever happened. So far, we've talked about light that is free almost from the start, but there is another twist you haven't dealt with yet. Not all photons get to leave their birthplace right away. Some are trapped inside stars for a long time, bouncing around for thousands or even hundreds of thousands of years before they ever escape into space. That raises a sharp new question. If some photons are ancient because they've travelled for billions of years, how old is the light that has been locked inside a star like the Sun before it even begins its final dash to Earth? How can sunlight be both only 8 minutes old and also tens of thousands of years old at the same time? You always hear the simple line, light from the Sun takes about 8 minutes to reach Earth, 150 million kilometres, about 93 million miles, at 300,000 kilometres per second, 186,000 miles per second. That part is clean and true, but it hides a much longer, much slower story inside the Sun itself, where photons are trapped for ridiculous amounts of time before they ever get near space. Deep in the core of the Sun, nuclear fusion is running non-stop. Hydrogen nuclei smash together to form helium, and in the process, a small amount of mass turns into energy. That energy first appears as very high-energy photons, gamma rays, but the core of the Sun is insanely dense, far denser than any material you've ever seen. A photon doesn't get a clear path out. Instead, it does what physicists call a random walk. It travels a tiny distance, gets absorbed by some particle, then re-emitted in a random direction, over and over again, like being stuck in the worst traffic jam in the universe. So while the last leg of the journey, from the sun's surface to your eyes, is a clean 8-minute straight line, the trip from the core to the surface is a chaotic shuffle that can take tens of thousands to hundreds of thousands of years. The sun is basically a photon prison, where light spends most of its life trapped, not flying. That raises a sharp question. If the core is flooding photons out in all directions, why does each one move so slowly in terms of net progress? What sets the pace of this escape? In the sun's core, the mean free path of a photon, the average distance it can move before hitting something, can be as small as a centimetre or less, fractions of an inch. The core is a plasma of protons, electrons and nuclei packed tightly together. Every time a photon travels that centimetre, it has a very high chance of being absorbed or scattered. When it's re-emitted, it doesn't keep its old direction, it shoots off in a new random direction. Now think about the size scale we're dealing with. The sun has a radius of about 700,000 kilometres, roughly 435,000 miles. A photon near the centre has to make its way out over that distance. Doing that in centimetre-sized steps, constantly changing direction, is painfully slow in terms of net outward progress. It's like trying to cross an entire city, but you're only allowed to take one small step at a time in a completely random direction, bumping into people every second. You're always moving fast in little bursts, but you're not getting far from where you started. When you add up this random walk, models suggest that the effective age of a typical photon that finally escapes from the sun's surface can be on the order of 10,000 to 100,000 years. The exact number depends on the details of the model, but the basic picture is clear. The energy that eventually becomes visible, sunlight, spends a very long time fighting its way through the interior. That leads to a slightly unsettling conclusion. The light hitting your eyes right now is not just a snapshot of what the sun did 8 minutes ago. It is the end product of energy that was created in fusion reactions that happened long before any human civilization existed, thousands to hundreds of thousands of years in the past. The 8-minute number is only the last, clean leg of the trip, the 150 million kilometre sprint through empty space. Before that, the same packet of energy was hidden inside the sun's interior, constantly being absorbed and re-emitted, changing form, changing direction, but still part of a slow outward leak of energy. Put that next to human timescales. Take 100,000 years, roughly the upper end of that photon age, and compress it into a single day. On that scale, the 8 minutes from the sun to Earth becomes less than a single second. Almost the entire life of the photon is spent inside the star. The flash of sunlight you see is just the final tiny fraction, the last step after an incredibly slow, blind, random walk through matter. And remember, the core where this starts is around 15 million Kelvin, about 15 million degrees Celsius, roughly 27 million degrees Fahrenheit. That's the environment that generates the energy you casually see as a sunny afternoon. So even at the scale of one ordinary star, light is often much older than the moment it escapes into space. The photons you see from stars are usually not instant signals of what just happened. They are delayed, processed outputs of long, complex journeys inside stellar interiors. Inside bigger, denser stars than the sun, the delays can be different, but the basic idea is the same. Energy gets trapped, bounced, and slowly leaks out. And that's not just about distance, it's about how the light itself changes as it moves. A photon that starts as a high-energy gamma ray deep in the core does not usually leave as a gamma ray. Each interaction can shift its energy, changing its wavelength. By the time the energy reaches the surface, a lot of it has been redistributed into visible and infrared light. You see a smooth yellow-white glow from the sun because that original high-energy radiation has been degraded and spread out across lower energies. That brings up the big question for the next step. If photons can age and lose energy just by bouncing around inside a star, what happens to light that doesn't just cross a star, but crosses the entire universe? Space itself is expanding under it. Wavelengths are stretching, energies are dropping. So how exactly does light age while it travels through billions of light years of expanding space-time And what does that do to the photons that started their journey near the beginning of everything? How can light lose energy without ever slowing down or bumping into anything? You've seen what happens to photons trapped inside a star. But what about light that is just crossing empty space for billions of years? The universe itself pulls another trick on it. And this is where cosmological redshift turns old light into a literal, physical thing, not just a poetic phrase. As the universe expands, the distances between galaxies that aren't gravitationally bound to each other get bigger. They're not flying through space like bullets, the space between them is stretching. Now picture a photon travelling through that stretching space. The wave pattern of that photon gets pulled along with the expansion. If the universe doubles in size while the photon is in flight, its wavelength doubles too. So a photon that started out with a wavelength of about 400 nanometers, which is violet light, might reach you at 800 nanometers, which is near infrared, or, if it has been stretched enough, at a wavelength of a millimeter, which is in the microwave range. This stretching is what cosmologists call redshift, because the light shifts toward the red and then beyond. It's not just a colour change, it is the universe literally writing its expansion history into the photons themselves. That raises a natural question: if the wavelength gets longer, is the light somehow slowing down on the way? Is the speed of light changing just because the universe is stretching? The answer is no. In a vacuum, photons always move at the same speed, about 3 times 10 to the power 8 meters per second, which is roughly 300,000 kilometers per second, or 186,000 miles per second. That part does not change. What does change is the energy carried by each photon. In physics, the energy of a photon is inversely related to its wavelength. Shorter wavelength means more energy, longer wavelength means less energy. You don't need the exact formula here. What matters is the trend: stretch the wavelength and the photon's energy drops. So over billions of years of travel through an expanding universe, an optical photon can lose orders of magnitude in energy. It doesn't slow down, it doesn't rub against a medium like air or water, it simply gets dragged by the expansion of space-time. The universe gets bigger, the wave gets longer, the energy goes down. The aging of light here is not just how long it has been travelling, it's a real physical degradation of energy tied directly to how much the universe has expanded. You can see this clearly in the numbers for the cosmic microwave background. When those CMB photons were released, the radiation field looked like a black body at about 3000 Kelvin. That's a hot glowing plasma. Today, the same photons fit a black body at 2.725 Kelvin. That is a temperature drop by a factor of about 1100. That same factor tells you how much the scale of the universe has grown since then, and how much the wavelengths have been stretched. A photon that started in the visible or infrared has been dragged all the way into the microwave range. For galaxies, we package this stretching into a parameter called redshift, written as Z. If a galaxy is at Z around 1, that means the universe was about half its present size when the light we see now left it. If a galaxy is at Z around 10, the universe was only about 1/11th of its present size. In other words, between emission and detection, the scale of the universe grew by more than a factor of 10, so you are literally detecting light that has been stretched by factors of 10, 100, even 1000 during its journey. The higher the redshift, the more extreme the stretching, and the older, in travel time, that light is. So how do you actually measure this redshift in practice? How do you convert a smeared, stretched spectrum into a real number that tells you age and distance? Astronomers use spectral lines as built-in markers. Atoms and ions produce light at very specific wavelengths. Hydrogen, for example, has a very important ultraviolet line called Lyman alpha at a known wavelength of about 121.6 nanometers. In a nearby galaxy, you would see that line at almost exactly that wavelength. In a distant galaxy, the entire spectrum is stretched, and that line appears at a longer wavelength. If you observe a galaxy and find that its hydrogen Lyman alpha line is now showing up at about 1.3 micrometers, which is 1,300 nanometers, That's almost 11 times longer. From that ratio, you infer a redshift of around 10. That single number, Z around 10, then tells you several things at once. It tells you how much the universe has expanded since that light was emitted. It tells you the look-back time, roughly how many billions of years the photon has been travelling. And with a cosmological model, it gives you a rough distance in billions of light years. So spectral lines become cosmic timestamps that link the physics of atoms to the history of the whole universe. At this point, you can see why talking about aging light is not just a dramatic way to describe old photons. Light literally ages in the sense that its physical properties change with time in an expanding universe. The wavelength grows, the energy drops, and the spectrum of the light field cools down. A photon that started its life in a hot, dense environment at high energy can end up billions of years later as a low-energy microwave photon carrying far less energy per particle than when it began. On top of that, the pattern of that redshift encodes the entire expansion history the photon has lived through. Different cosmological models, different contents of dark energy and dark matter give you different relationships between redshift, distance, and look-back time. By measuring redshifts and comparing them to how bright and how large objects appear, cosmologists can reconstruct how fast the universe was expanding at different times. In other words, the age of the photon is not just how long it has flown, it's a record of how the universe behaved while it was in flight. So when a photon finally lands in your detector, or in the sensor of a telescope, you're not just catching a simple piece of light. You're catching something that has been physically transformed by billions of years of cosmic evolution. Its energy is lower, its wavelength is longer, and its spectrum has been shifted, all because the universe grew around it. It carries, in its final state, the fingerprint of that growth. But if light can be stretched, cooled, and aged like this, the next question is obvious and much sharper. Is there a hard limit to how old a photon can be when it reaches you? Is there a wall beyond which no amount of better technology can see, no matter how big your telescope is? To answer that, you have to look at the horizons built into space-time itself and face the fact that the universe has a maximum visible age written right into its structure. Is there a hard edge to how far you can ever see, even in principle, even with infinite patience and a perfect telescope? Not just a practical limit, but a built-in wall in the universe itself. There is, and cosmologists call it the particle horizon. The particle horizon is the maximum distance from which light has had time to reach you since the Big Bang. Take the entire history of the universe, 13.8 billion years of time, and ask a simple question. From how far away could a photon have started and still make it to me by now, given that the universe is expanding while it travels? When you do that calculation with our best cosmology, you get a current distance of about 46 billion light years. In metric, that's around 4.3 times 10 to the power 26 meters. In imperial units, that's roughly 270 billion miles. Anything farther away than that is causally disconnected from you. Light from those regions has not had time to arrive and never will, because the expansion of space keeps pushing them away faster than light can close the gap. You cannot see them, you cannot send a signal to them, you cannot influence them. They might as well be in a separate reality as far as you're concerned. That's not a technology problem, that's a structure of space-time problem. So if there is a maximum distance like that, what does that look like when you think about the oldest light itself, the CMB you keep coming back to? The cosmic microwave background does not come from a single point. It comes from a whole shell around you, called the surface of last scattering. That's the set of places where photons last interacted with matter before streaming freely. In today's coordinates, that surface sits at about the same 46 billion light years away from us in every direction. So you can picture yourself at the center of a huge sphere with a radius of 46 billion light years, and on that sphere is where the CMB is being emitted. Not now, but as you see it now. Double that radius and you get a diameter of about 92 billion light years. In meters, that's around 8.7 times 10 to the power of 26. In miles, about 5.4 times 10 to the power 27. That sphere is made of the oldest light we can ever observe with photons, the same cosmic microwave background you measure at 2.7 Kelvin. Every direction you look, your line of sight ends on that shell. Inside that shell, you see galaxies, clusters, stars. Outside that shell, you see nothing with light, because you're looking back to a time when light was still trapped in plasma. And this is where a lot of people get tripped up, because your brain wants to mix up years and light years and treat them as the same thing. They aren't. When you say we see back 13.8 billion years, you're talking about look-back time, how long the light has been travelling. The light from the CMB has a look-back time of about 13.8 billion years, but the stuff that emitted that light is not 13.8 billion light years away in current distance. While the photon was in flight, the universe expanded. That region has been dragged outward by the general expansion of space, so the light travel time is 13.8 billion years, but the current distance to the emitting region is about 46 billion light years. You see back 13.8 billion years, not out 13.8 billion light years. That mismatch between travel time and present distance is one of the main reasons people say things like light older than the universe, or distances bigger than the age of the universe, and feel like something is wrong. The confusion comes from forgetting that space itself is stretching while the light moves. If you try to push past that CMB wall with light, you hit a more fundamental problem. Before recombination, the universe simply did not let photons move freely over large distances. In that earlier era, before about 380,000 years after the Big Bang, the universe was a hot plasma filled with free electrons and protons. A photon could not travel very far without hitting an electron. Its mean free path, the average distance between interactions, was tiny, on the order of centimeters, fractions of an inch, even though the universe itself already spanned light years. The whole cosmos was like a glowing fog where light was constantly scattered. There was no way for a clean image to form, no way for a photon to carry information over cosmological distances without being scrambled. That's why the CMB is a hard wall for electromagnetic observations. Earlier times absolutely existed. There was inflation, there was the quark-gluon plasma, there were the very first nuclear reactions, but none of that is directly visible with photons. Light from those epochs never got a chance to travel freely all the way to you. The universe only becomes transparent at recombination, so that is the earliest snapshot you can ever get in light, no matter how advanced your instruments become. So now you're stuck with a simple but heavy conclusion: there is a maximum age that any photon can have when it reaches you. At most, it can have been travelling since about 380,000 years after the Big Bang. Add that travel time to now, and you get something just under the full 13.8 billion year age of the universe. You'll never detect a photon that has been freely travelling for 20 billion years, because the universe itself is not that old, and you will never detect a photon that has been travelling for the full 13.8 billion years, because for the first 380,000 years, photons were trapped. That cap is not guesswork or a loose estimate. It comes straight from the physics of recombination, the measured properties of the CMB, the expansion history we get from redshifts, and the way radiation interacts with matter. It is baked into the way space-time plus plasma plus radiation behave together. So when you hear people say this light feels older than the universe, what they are really bumping into is this horizon. You're interacting with photons that are almost as old as time itself, that have survived every phase the universe has gone through, but you can never go past that limit using light. That tension is what makes the whole picture feel uncomfortable. There is more history behind that wall, but your main messenger, photons, cannot cross it. And that immediately raises a new, sharper question. If light hits a hard wall in how far back it can show you, is there any way at all to get information from earlier than the oldest photons, from times closer to the Big Bang than recombination? To reach that deeper layer of the universe's past, you have to stop relying on light and switch to messengers that barely interact with matter at all. Particles and waves that started moving even earlier and almost never get stopped. If photons aren't actually the oldest messengers we can tap into, what beats them? If the oldest light you can see comes from 380,000 years after the Big Bang, but the universe itself started earlier than that, something else has to be carrying information from those first moments. That's where neutrinos and gravitational waves come in, and they push old signal to a whole new level. First, neutrinos. If photons are the oldest light, neutrinos are even older messengers. Neutrinos interact ridiculously weakly with matter. They basically ignore almost everything. Because of that, they decoupled from the hot plasma of the early universe way earlier than photons did, about 1 second after the Big Bang. At that time, the universe's temperature was around 10 billion Kelvin, far hotter than any star core you can imagine today. From that point on, those relic neutrinos have been freely streaming through space, almost never colliding with anything. Calculations say there should be roughly 300 of these Big Bang neutrinos in every cubic centimetre of space. That's a tiny cube, 1 centimetre on each side, less than half an inch. That means billions of these relic neutrinos pass through the area of your fingertip every second, and you feel nothing. Each one has been flying since the universe was about a second old, so in terms of age, they're almost as old as the universe itself, older than any photon you will ever detect. So if there is this massive sea of ancient neutrinos all around you, why haven't you seen them the same way you've mapped the cosmic microwave background? The short answer is they are brutally hard to detect. Neutrinos hardly ever interact. To see even a few of them, you need enormous detectors, like tanks of ultra-pure water or special fluids buried deep underground, with photodetectors waiting for the rare flashes of light triggered when a neutrino finally hits something. That works for higher energy neutrinos from the Sun or from supernovae. But the relic neutrinos from the Big Bang are extremely low energy, much colder than the CMB photons, and their interaction probability is tiny. So far, we haven't directly imaged or mapped this cosmic neutrino background the way we have the CMB. Instead, we infer that it exists from indirect effects. Big Bang nucleosynthesis, the process that set the hydrogen and helium ratios, is sensitive to how many neutrinos there were and how they behaved. The CMB itself, in its detailed pattern of fluctuations, also carries hints of neutrinos. Those lines of evidence together strongly support that the relic neutrino background is real, but we do not yet have a neutrino sky map like we do for the microwave background. If neutrinos take you back to about 1 second after the Big Bang, is there any way to reach even earlier than that? That's where gravitational waves come in. Gravitational waves are ripples in space-time itself, not in a field moving through space-time. They can be generated by violent events, like merging black holes, but also by processes in the very early universe, including inflation, the rapid expansion that might have happened around 10 to the power minus 36 seconds after the Big Bang. Inflation would have taken tiny quantum fluctuations and blown them up to cosmic scales. Those fluctuations in space-time could leave behind a background of primordial gravitational waves. Unlike photons, gravitational waves barely care about dense plasma or matter. They can pass through almost anything with very little interaction. That means in principle they can carry information straight from epochs that are completely hidden to light and even mostly hidden to neutrinos, from fractions of a second after the Big Bang, or earlier all the way to now. Right now our detectors are not tuned to that primordial background. Today's instruments like LIGO and Virgo are sensitive to much later and more local events, merging black holes and neutron stars. Those events are still billions of light years away, which is impressive by itself, but they aren't from the early universe, they're from much more recent cosmic history. The waves they detect last fractions of a second in the data, but the sources are compact objects that formed long after galaxies and stars existed. However, future detectors, both upgraded ground-based ones and new space-based missions, are being designed to probe lower frequencies and much fainter signals. If we can get instruments sensitive enough, we might be able to detect the background hum of primordial gravitational waves, like hearing the faint roar from the first moments of the universe. That would give us direct data from epochs way older than the oldest light, potentially all the way back toward the inflation era. So when you ask, What is the oldest signal we could ever hope to detect? You have to be precise. If you mean light, photons, the answer is fixed by recombination and the CMB. That ceiling is about 13.8 billion years of travel minus 380,000 years. If you widen your view to all messengers, the story changes. Relic neutrinos have been on the move since about 1 second after the Big Bang. Primordial gravitational waves, if we can detect them, could have been travelling since unimaginably tiny fractions of a second after the beginning. But in everyday language, when people say light older than the universe, they are not thinking about all these technical layers. They're reacting to how absurdly ancient these signals are compared to anything human. The neutrinos crossing your body, the CMB photons washing through you, the gravitational waves that might be rippling past you right now, all of that started long before Earth formed, long before the Sun, long before the Milky Way looked like a proper galaxy. So once you accept that there are messengers older than any structure you can see, and even older than the oldest light, you have to zoom back out and ask a different question. If the oldest signals carry the initial conditions, how did all the younger, visible structures we actually look at, galaxies and clusters and the cosmic web, grow out of those tiny seeds in the first place, and how do they end up bending and reshaping the very ancient light that passes through them? How can something that didn't even exist when light was created end up steering that light billions of years later? That's exactly what happens with galaxies, clusters, and the giant cosmic web. They are late arrivals that reshape ancient photons that were already on the move long before those structures formed. On the largest scales, the universe is not just a random sprinkle of galaxies, it's organized into a structure called the cosmic web. You have filaments of galaxies and gas that can be hundreds of millions of light years long. That's on the order of 10 to the power 24 meters, which is tens of sextillions of miles. These filaments connect at big nodes, which are galaxy clusters, and in between are huge voids that are relatively empty. None of this was there in the beginning. These giant structures took billions of years of gravitational evolution to grow out of the tiny overdensities you saw as temperature ripples in the CMB. So what does that timeline actually look like? Those little density bumps in the early universe, the 0.001% extra matter here and there, slowly pulled in more mass. Dark matter, which doesn't emit light but does feel gravity, formed halos first. Gas fell into those halos, cooled down, and eventually formed stars. Over time, small objects merged into bigger ones, and the cosmic web slowly sharpened. You're looking at a process that runs over most of the 13.8 billion year history of the universe, starting from almost smooth conditions and ending with filaments spanning hundreds of millions of light years. Now compare that with when the first galaxies appear. The earliest galaxies we think exist show up at redshifts around 10 to maybe 15, which means we see them when the universe was only a few hundred million years old, maybe 300 to 400 million years after the Big Bang. These are small young systems, not the giant spirals and massive clusters you see today. The big heavy galaxy clusters and superclusters, with thousands of galaxies bound together, took much longer to assemble. We're talking several billion years of mergers and accretion as smaller groups fell together and dark matter halos combined. So when you look at a present-day galaxy cluster, a structure that might be 10 million light-years across or more, you are looking at something that formed long after the first light was already free and travelling. It is vastly younger than the photons that originally traced the tiny overdensities in the early universe. Here's the key point tying it back to the older light idea. CMB photons have been travelling freely since 380,000 years after the Big Bang. While they were moving through space, gas was cooling, dark matter halos were forming, stars were igniting, small galaxies were merging into bigger ones, and clusters were assembling over billions of years. By the time today's large spiral galaxies like the Milky Way reached anything like their current form, those CMB photons had already crossed billions of light years in co-moving distance. So the light didn't wait for galaxies to form, it was already out there moving, while the entire large-scale structure of the universe slowly took shape. When we detect those photons today, we are seeing light that started in a galaxy-free universe, then passed through a universe full of galaxies. Now bring gravity back into the picture in a more direct way. Massive galaxy clusters don't just sit there, they warp space-time around them. According to general relativity, mass curves space-time, and light follows the curves. That means a big cluster can act like a gravitational lens, bending and magnifying light from objects behind it. We actually see this in images, distant galaxies stretched into arcs and rings around foreground clusters. And it's not just optical or infrared light, the same effect applies to CMB photons. As ancient CMB light passes by massive structures, its path is deflected slightly. That lensing distorts the CMB pattern in measurable ways. You literally have photons that were released 380,000 years after the Big Bang, flying for billions of years, and then having their path tweaked by clusters that only formed billions of years after the photons started their journey. That's the weird core of this whole section. Some of the light you see today is being bent and focused by objects that did not exist when that light was born. The photon's journey starts in a universe with no galaxies, no clusters, just a nearly uniform plasma. It travels while structure slowly builds up. Much later, when a massive cluster finally forms in its way, gravity deflects the photon, maybe sends it toward your telescope instead of past it. The final direction that ancient photon takes, the direction that decides whether you see it or not, is controlled by matter that assembled billions of years after the photon was emitted. So you end up with this layered picture, ancient light shaped by young structures. The light encodes the conditions of the early universe in its spectrum and its redshift, but its path and apparent position in the sky are influenced by structures that grew up much later. Time and space are mixed together in a way that is not intuitive at all. And if galaxies and clusters can bend and redirect photons that started in a much younger universe, there's another twist you haven't looked at yet. Many of the sources that created the light we see today are gone. The stars have exploded, the quasars have shut down, the gas clouds have dispersed, but the photons they emitted are still in flight, still arriving. That raises the next question. How often are you looking at light that outlived the thing that made it? And what does that really mean for how you think about old and young in the universe? How can you look at a star that doesn't exist anymore? Not in a poetic way. Literally, the star is gone. The light is still arriving. This is where light outlives its source, stops being a phrase and becomes a very literal description of what your telescopes see. Take a massive star that ends its life as a supernova. In its final moments, its core collapses and the outer layers explode outward. For a short time, that explosion can outshine an entire galaxy. For days or weeks, the brightness jumps by a factor of millions. But the star itself is done in seconds. The inner core becomes a neutron star, a black hole, or just disappears into expanding gas. The engine that produced that flash is over almost as soon as it starts. The photons, though, don't care. Once they're emitted, they just go. They leave the dying star, cross interstellar space, then intergalactic space. If the supernova went off in a galaxy billions of light years away, those photons can travel for billions of years before anyone on Earth builds a telescope sensitive enough to detect them. By the time a detector on some future observatory records that flash, the material from the explosion has already spread out, cooled, mixed into the host galaxy, maybe even formed new stars and planets. The original star is long gone, but its light is still turning up as fresh data. The same logic hits even harder when you look at quasars. A quasar is a supermassive black hole at the center of a galaxy, feeding on gas. As matter spirals in, it heats up and emits enormous amounts of radiation. A single quasar can shine thousands of times brighter than a normal galaxy, outradiating hundreds of billions of stars combined. But it doesn't necessarily stay on forever. Once the black hole has eaten most of the nearby gas, the fuel supply drops, and the quasar can fade or shut off. The photons it emitted while it was active, though, are gone. They're already on their way across the universe. There are quasars we detect today whose central engines have probably been quiet for billions of years. We're seeing them in their active phase only because the light from that time is still in transit. If you could jump to their actual location now, you might see a perfectly ordinary-looking galaxy with no glaring quasar at all, only a massive black hole sitting quietly at the centre. Scale that idea up and you get the extragalactic background light, the EBL. This is a diffuse glow that fills the universe in optical and infrared wavelengths. It's not concentrated in one direction, it's the sum of all the light ever emitted by all the stars and galaxies over cosmic time, minus what got absorbed and re-emitted at other wavelengths. You can think of it as the integrated light record of the universe's history. A big chunk of the EBL comes from sources that aren't in the same state anymore. Some of those stars have died, some of those galaxies have merged, some of those quasars have shut off, some gas clouds have turned into new stars and planets. The original configurations that produced the photons don't exist anymore. The photons, though, are still travelling, still carrying the imprint of what those systems were like when they emitted that light. At the level of a single photon, this gets very precise. A photon carries information about the physical conditions at the moment it was emitted. Its energy tells you something about the temperature and processes in the source. Its direction tells you where in the sky the source was. Its polarization can reveal magnetic fields or scattering process. Even if the source has since exploded, collapsed, merged, or faded, you can still read those conditions from the photon when it finally hits your detector, billions of years later. So when you stare at a distant galaxy, you're not seeing the galaxy as it exists now. You're reading a stream of photons that were launched when that galaxy was younger, maybe in a completely different state. The galaxy might have doubled its mass since then, or lost its gas, or gone through a major merger. The light you see is older than the current version of the object. That's the point. Even on these smaller scales, light does not care about the lifetime of the source. It doesn't shut off just because the star dies or the quasar fades. Once emitted, it keeps going until it hits something. You routinely observe photons that are older than the current state of whatever produced them. In many cases, the original configuration is gone, but the photons are still arriving. In that sense, light doesn't just survive the universe's history, it outlives the systems that made it. It outlives stars, outlives flares, outlives quasar phases, sometimes outlives entire galaxy structures as they merge and change shape. And that leads to a deeper question that goes beyond just age. If light keeps this kind of long-term record, what does that say about the direction of time itself? About the fact that the universe evolves from hot and bright to cold and dim, and that photons are one of the main ways that irreversible change gets written into reality? Why does old light feel so connected to the direction of time itself? It's not just that photons are ancient, it's that every time something hot shines into something colder, the universe quietly moves forward in one direction, and it never rewinds. Anytime a hot object radiates light into a cooler environment, entropy goes up. That's the basic rule. Take a star or a cloud of hot gas, or the bright disk of material spiraling into a black hole. All of them are hotter than their surroundings. They pour out photons, spreading their energy into a much bigger volume at lower temperature. That energy doesn't disappear. It gets diluted into low-temperature background light, into things like the cosmic microwave background and the extragalactic background light. So just by shining, stars are pushing the universe toward higher entropy. A star takes concentrated energy inside its core and leaks it out as light into space. Once that radiation is out there as a thin bath of low-energy photons, you're not going to collect it all back and stuff it into one hot ball again without spending even more energy. The process is effectively one way. More photons at lower energy, more ways for the universe to arrange itself, higher entropy. This plugs straight into how the universe itself changes over time. Early on, the radiation field was hot, bright, and dominated by short wavelengths, like ultraviolet and visible light. As the universe expanded, the wavelength stretched. As stars and galaxies emitted more light, those photons then got redshifted too. Over billions of years, the entire photon population shifted toward longer wavelengths and lower energies. Now, most of the photons in the universe are not high energy, blue or ultraviolet. They're low-energy microwave and radio photons. The CMB alone, at about 2.7 Kelvin, is a huge reservoir of low-energy radiation. On top of that, you have the extragalactic background light in the infrared and optical, much of which has also been redshifted. These photons are fossils of much hotter, brighter epochs. They used to be part of intense local radiation fields near stars and hot gas. Now they're thin, cold backgrounds. So the story is simple but not gentle. You go from hot, bright and blue to cold, dim and red. Expansion stretches wavelengths. Processes like scattering and re-emission push energy down the spectrum, and entropy climbs as the same total energy is smeared out into more and more low-energy photons. Every time you count particles in the universe, this asymmetry jumps out. There are about 1 billion photons for every proton. For every single proton in all the stars, gas clouds, planets and people, there are roughly 1 billion photons flying around. That ratio isn't random. It comes from early universe physics, from how matter and antimatter annihilated, from how much energy was left in radiation after that phase, and from how much baryonic matter survived as protons and neutrons. The exact number ties into processes like baryogenesis and reheating after inflation, but the takeaway is clear: the universe is dominated by radiation in terms of sheer particle count. Matter and dark energy dominate the energy budget today, but in terms of how many pieces are flying around, photons crush everything else. That huge photon population is a direct product of how the early universe evolved and how entropy grew. Now look at what those photons actually represent. The light produced by stars, galaxies and hot gas is not just brightness, it's a record of irreversible processes. Nuclear fusion in stars converts hydrogen into helium and heavier elements and releases energy as photons. Accretion disks around black holes radiate as gas falls in and loses gravitational energy. Shockwaves, collisions, stellar winds, all of them generate radiation as they turn ordered energy into heat and then into light. Once those photons are emitted, they mostly don't come back. They fly off, redshift, and eventually join the general background. You could, in principle, capture a tiny fraction with a solar panel or a planet's atmosphere, but on cosmic scales, almost all of that radiation just spreads out and cools. The increasing photon count and dropping average photon energy are part of the way the universe's arrow of time shows up in physics. Early universe, fewer, hotter photons in a smaller volume. Late universe, more, colder photons in a much larger volume. That's why photons act like a memory system for the universe. Each photon is a snapshot of an irreversible event. A particular fusion reaction in a star, a specific burst from a supernova shockwave, a pulse of energy from a quasar outburst. You can't run those processes backward in any realistic way, but you can still detect the photons and see what happened. Matter, by contrast, is messy. Stars die, galaxies merge, gas clouds collapse, form stars, get blown apart, then cool and form new stars again. Planets get destroyed or ejected. The same atoms get reused over and over in different structures. If you look at matter now, you're seeing the end result of many steps of rearrangement. It's hard to decode the full history just by looking at where the atoms ended up. Radiation is different. Ancient photons keep flying. They don't merge into larger particles. They don't get recycled in the same way. They can scatter, redshift, and get absorbed, but a huge fraction of them simply cruise through the universe, carrying their original information. That's why when cosmologists want to reconstruct the universe's past, they lean so hard on light, the CMB for the early universe, the EBL and galaxy light for the Middle Ages, supernova and quasar light for more recent cosmic history. Put all of that together, and you get this picture: the universe's arrow of time is written into light. The early universe was hot, dense, and relatively smooth. Over time, structure formed, and at the same time radiation spread out and cooled. Entropy climbed and photons multiplied. Old light tells you which way time has flowed, from hot to cold, from smooth to clumpy, from simple to complex. But that brings you back to the tension that started this entire video. If photons are the carriers of this history, and some of them are almost as old as the universe itself, what exactly are you saying when you talk about light that feels older than the universe? Are you actually breaking the rule that nothing can be older than the cosmos? Or are you just using sloppy language for something very precise but still mind-bending? To resolve that, you have to pin down in strict terms what age of the universe really means, what age of a photon really means, and why the phrase older than the universe is technically wrong but emotionally accurate. That's where all the timelines, distances, and redshifts you've built up finally come together. How can you talk about light that feels older than the universe without actually breaking physics? This is where you have to be very strict about what age even means in cosmology, otherwise the words start doing things the math never does. The age of the universe, that 13.8 billion year number you keep hearing, has a precise definition. It's the time that has passed since the Big Bang, measured along your world line, basically along the path you take through space-time as a typical observer in the expanding universe. That's the master clock. Nothing that exists inside this space-time can have an age larger than that. Not a star, not a rock, not a black hole, not a photon. A photon's age is just how long it has been travelling since it was emitted. For a CMB photon, that travel time is about 13.8 billion years, minus those first 380,000 years when light was trapped. So roughly 13.7996 billion years. That's incredibly close to the age of the universe, but still under it. There is no photon that has been freely travelling for 20 billion years, because the universe has not existed for 20 billion years. So in strict terms, nothing is older than the universe. The universe sets the upper limit, and everything else sits below that ceiling. So why does the phrase light older than the universe still stick in people's heads? Why does it feel like you're seeing something that outruns its own origin? When people say that, they're reacting to how extreme the situation is. You're detecting a particle of light that has been in flight for almost the entire history of everything. It left a universe with no stars, no galaxies, no planets, no Milky Way, no sun and no Earth. And it is hitting you now, after all of that has already happened. That feels like the photon is not just old, it's somehow outside the normal timeline of things you're used to. Older than the universe as you recognize it in your daily mental picture, which is galaxies, stars, planets, and you. There's another source of confusion, and it's baked right into how we talk about distance. You use light year as both a distance and an implied time. If something is 10 light years away, you say the light took 10 years to get here, and that is fine in flat, non-expanding space. But in an expanding universe, the link between distance in light years and age in years is not that simple. Take a CMB photon. The look-back time, how long the photon has been travelling, is about 13.8 billion years. But the region that emitted that photon is now about 46 billion light-years away in current distance. So you get this weird pair of facts. The universe is 13.8 billion years old, the light has been travelling for about that long, and yet the source is now 46 billion light-years away. If you skip the expansion part, that sounds possible. Like light has gone further than the age of the universe allows, so your brain jumps to, okay, so maybe this light is older than the universe. It's a shortcut your intuition uses to patch a mismatch it doesn't fully understand. Once you put expansion back in, the paradox disappears. The photon has only had 13.8 billion years to move, it has not broken the speed of light, it has not outrun the universe. While it was travelling, space itself stretched, so the distance to its origin grew. You see back 13.8 billion years in time, but out 46 billion light years in present distance. Those are different quantities, and mixing them is where a lot of the older than the universe talk comes from. So what is the precise, correct way to say what you actually mean, without breaking physics, but still capturing how extreme this is? You say this, you are seeing light that has been travelling for almost 13.8 billion years, from a time before there were stars, galaxies, or planets. The photon is older than almost every structure you can point to in the universe. It's older than the sun, older than the Milky Way in its current form, older than any planet, older than any living thing. It is not older than the universe itself, but it is older than the universe as you normally picture it, The universe full of luminous structure. That's the version that is technically correct and still hits hard. It doesn't violate the rule that nothing can be older than the universe, but it doesn't soften how extreme these timescales are. It keeps the shock without the error. And here's the key part. Fixing the language doesn't make the reality less wild. You are sitting on a rock orbiting a middle-aged star in a galaxy that took billions of years to assemble. All of that formed long after primordial photons were already streaking across space. By the time your galaxy really took shape, there were already ancient CMB photons everywhere. By the time the sun lit up, those photons had been travelling for over 9 billion years. By the time Earth cooled, they had crossed distances measured in tens of billions of light years in today's coordinates. Your whole local setup, your universe in the day-to-day sense, is a late arrival. You live in a universe that was already full of radiation, full of old photons and relic neutrinos, full of the imprints of early quantum fluctuations, long before your corner ever formed. You are literally catching the tail end of signals that have been running since almost the beginning. And that leads to the last twist in this chain. It's not just that old light exists, it's that you, right now, are part of how that light story ends. Your eyes, your detectors, your telescopes, your atmosphere, even your skin, are places where these multi-billion-year journeys finally stop. So the next question is, if ancient photons are everywhere, how much of that are you personally actually interacting with, sitting in your room, walking outside at night, or pointing even a small amateur telescope at the sky? How much ancient light are you personally picking up just by looking around? Not a telescope, not a lab, just your own eyes and your own body. The answer is way more than your day-to-day sense of time would ever guess. Your eyes are insanely sensitive. In a dark environment, they can respond to just a few photons hitting your retina. Some of those photons come from nearby stars in the Milky Way, a few tens or hundreds of light years away. If a star is 300 light years away, the light landing on your eye tonight left that star about 300 years ago. Before any modern technology, before electricity was normal, before a lot of today's countries even existed in their current form. Point your eyes at Andromeda, the big spiral galaxy that you can just barely see as a faint smudge if you have dark skies. Andromeda is about 2.5 million light years away. That means the photons that hit your retina tonight left that galaxy 2.5 million years ago. Back then, early humans were just starting to use stone tools. No cities, no writing, no agriculture, just small groups of hominins trying to survive, while those photons were already in flight toward where you are now. So with naked eyes, you're already doing time travel on the order of hundreds to millions of years, just by glancing at the night sky. But once you add even a small telescope, the timescales you personally touch ramp up fast. A modest backyard telescope with a mirror around 20 centimeters across, roughly 8 inches, lets you collect more light and see fainter objects. You can pick up galaxies tens of millions of light years away. If you see a galaxy 50 million light years away, the photons that your telescope collects have been travelling for 50 million years. That's older than the entire human species. Homo sapiens has only been around for something like a few 100,000 years. So with a simple amateur setup, you're intercepting individual packets of information that started moving long before anything like you existed. From your perspective, you take a few minutes to set up, aim and look through the eyepiece. From the photon's perspective, it's the end of a 50 million year trip across intergalactic space, a journey that started before humans, before mammals spread the way they have now, before Earth's continents look like they do today. Now scale up to professional observatories, big ground-based telescopes with mirrors 8 to 10 meters across, about 26 to 33 feet, and space telescopes like Hubble and JWST collect vastly more light. They can detect galaxies billions of light years away. When they point at a deep field and expose for hours, the image that comes out is built from photons that have been travelling for 1 billion, 5 billion, 10 billion years. Some of those photons left their sources when the universe was just a few billion years old, some when it was even younger. Every exposure a big observatory takes is not just a picture, it's a data set of ancient signals. A single image might contain galaxies at many different distances, which means many different ages. Some of the light in that image has travel times of almost 13 billion years, nearly as old as the universe itself. When astronomers pull that image up on a screen, they are not looking at a snapshot of now, they are looking at a layered history of the universe in one frame. But even if you never look through a telescope, you're still interacting with old messengers all the time. Your body is constantly crossed by cosmic microwave background photons, relic neutrinos and cosmic rays. You don't feel it, but it's happening every second. CMB photons pass through you from every direction at a rate of trillions per second. Each one has been travelling since the universe was only a few 100,000 years old. Relic neutrinos, from about 1 second after the Big Bang, stream through you on top of that, along with higher energy neutrinos from the Sun and from cosmic events. Cosmic rays, which are mostly high-energy protons and atomic nuclei, slam into the atmosphere at close to the speed of light, creating showers of particles, some of which reach you at ground level. You're not just in the universe like someone sitting in a room, you're immersed in a constant flux of ancient messengers that started their journeys long before Earth's crust cooled, long before the solar system formed, long before any life existed. Your body is being crossed by signals from the early universe, whether you care about cosmology or not. Think about how these journeys end. Photons don't last forever in flight. Eventually, they hit something. They might get absorbed in an atom in the atmosphere, turned into heat. They might get captured by a detector on a satellite, converted into a voltage. They might hit your retina and trigger a chemical change that your brain interprets as I see a star. In every one of those cases, you are part of the final step. You are the last page in the story of those photons. They spent billions of years moving through space, avoiding interactions, and then their journey stops in your eye, your camera, your telescope, or your planet's air. When you look at a star or a galaxy or a faint glow in microwaves on a screen, you are literally reading the oldest chapters the universe has written in light. You are consuming the end of a process that started almost at the beginning. So take a step back and connect this to everything you've heard so far. The photons are almost as old as the universe. They carry the imprint of expansion. They have watched structure form. They have been bent by galaxies and clusters that formed long after they were born, and now they are ending in you. You're not separate from the story, you're one of the destinations. That leaves one last thing to do. You need to close the loop, pull all of this together into a single clear idea. If nothing can be literally older than the universe, but light can be older than almost everything you see, what does that really say about where you are in cosmic time, and what kind of universe you actually live in? So what is the honest, cleaned up version of that original wild idea, without breaking any physics? Here it is, straight. You live in a universe where light is almost as old as time itself, and much older than nearly everything you casually call the universe. The photons you detect today, with your eyes or with a telescope or with a satellite, started their journeys in eras when there were no galaxies, no stars, no planets, no life, nothing you would recognize as a sky. They have been in flight since the universe was hot, dense, and completely alien to your everyday picture. That means when you look at the universe, you're actually looking at two very different things at once. On one side you have structures, galaxies, clusters, stars, planets, you. On the other side you have messengers, photons and neutrinos and gravitational waves that have been moving almost since the beginning. Structures form late, change, merge and disappear. The messengers are out there first and they keep going, carrying information forward. So line it up as a simple age ladder. At the very top, oldest of all, you probably have primordial gravitational waves if inflation really happened. Those would come from times around 10 to the power minus 36 seconds after the Big Bang, unimaginably early. Next come relic neutrinos, which have been flying since the universe was about 1 second old, at temperatures around 10 billion Kelvin. After that, you get the cosmic microwave background photons, released when the universe was about 380,000 years old, at about 3000 Kelvin. Then much later you get the first starlight and the first galaxies, a few 100 million years after the Big Bang. After that, the big galaxy clusters and superclusters that build over billions of years. Then the Sun, at around 9 billion years into the universe's history, and the solar system and Earth, and finally right near the very end of that chain, you. Light sits near the top of that hierarchy. It is one of the oldest active players in the game, the senior citizen in a room full of young structures. You might ask, how much of this is solid and how much is just a nice story? The answer is, the numbers are coming from hard data. The 13.8 billion year age of the universe is not pulled out of thin air. It comes from precision cosmology, matching measurements of the cosmic microwave background, galaxy clustering and the present expansion rate. The 2.725 Kelvin temperature of the CMB is measured directly, with instruments that compare the sky to laboratory black bodies and find agreement to better than 1 part in 10,000. The redshifts of distant galaxies are not guesses either. They're measured spectroscopically. You see spectral lines, like hydrogen's Lyman alpha, at stretched wavelengths, and you compute the redshift from that. From redshift and a well-tested cosmological model, you then calculate look-back times and distances. That's how you get to this galaxy is more than 10 billion light-years away in look-back time. Or, the region that emitted the CMB is now roughly 46 billion light-years away in comoving distance. Distances like 10 to the power 26 meters, 10 to the power 27 miles are not marketing lines. They drop out of the math when you feed in data from real telescopes. So the story sounds dramatic, but it's anchored in measurements. No step here is because it sounds cool. It's because the data leave you almost no choice. What does that do to your basic intuitive idea of what the universe is? Most people think the universe is what you see around you right now. The Milky Way, nearby galaxies, the Sun, planets, maybe some galaxy cluster images they've seen online. That picture is not wrong, but it's extremely incomplete. The deep truth is that the universe is a 13.8 billion year process. It's not a static thing, it's a long history, and most of that history is not in the current arrangement of matter, it's in the radiation that has been flying around the whole time. Those ancient photons are not background decoration, they are the record. The universe started hot, dense, and almost smooth. Small fluctuations grew into galaxies and clusters. While that was happening, radiation was spreading out, losing energy, and piling up into backgrounds like the CMB and the extragalactic light field. By the time your corner of the cosmos formed, the universe was already full of these old signals. Your galaxy, your star, your planet are just recent details on top of a story that's already 13.8 billion years deep. So when you hear a light older than the universe, you now know the precise version. You're not breaking physics. You're dealing with photons that have been travelling for almost the full age of the universe, released before stars, before galaxies, before planets, and still arriving now. They're not older than the universe's clock, but they are older than almost everything you can point to. Older than the Milky Way, older than the Sun, older than Earth, older than every living thing. And you are not just a spectator to that, you are made of atoms that were forged in stars, cooled in gas clouds, assembled into planets, and eventually turned into living tissue. Those atoms are now intercepting photons that have been moving at about 300,000 kilometers per second, 186,000 miles per second, for billions of years. Your eyes, your instruments, even your skin are where some of those journeys end. So the next time you step outside at night, don't reduce it to, I'm looking at some stars. You are catching the last stop of photons that have been on the road for millions to billions of years, launched in a universe that was hot, dense, and unrecognizable compared to what you see now. You are, in a strict scientific sense, a collection of atoms reading the universe's memory written in light, right at the edge of how old a signal can be without being literally as old as time itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.